Okay, so, Bohr came up with this model, stationary states and so forth and so on. But, we have to explain, where does it come from? I mean, he just said, look, there has to be stationary states because the atom is stable, which is totally correct, but that's not enough. Okay, we have to come up with a way of, where do these come from? Where do these energy values come from? What are the values of the radius of these stationary states? We have to, explore this whole idea of a stationary state. Okay, so well, first of all, let's think back of Physics 121. Remember this? And so, I mean, here, we had stationary states, right? If we threw it with not enough energy, it didn't go all the way around. Threw it a bit more, hit the ground. If we threw it with just the right force, so it had just the right energy, it orbited the Earth, right? And so you can think of this as a stationary state. So we've seen this before, right? And again, this ball, or whatever, this didn't crash into the Earth because it had the right speed. And we calculated that back in 121. So let's just do it for the hydrogen atom, see what we come up with. All right, so there's a hydrogen atom, simplest atom there is, right? You have a proton there in the nucleus, and you have an electron. That's it. All right, so let's do some classical physics. 121. So this is circular motion, right? The electron is orbiting the proton. Circular motion, remember that? So for circular motion, we say the sum of the radial forces equals mv squared over r. Okay, now that was the part that's always true. But as we learned in 121, our job is to say, okay, that's true, but what are the actual radial forces, right? Normal force, gravity, friction, I mean, who knows? Electric, magnetic. All right, so here, what's the force between a positive proton and a negative electron? Well, it's obviously electrical force, right? It's the electrical force. Now, if you didn't have Physics 220, don't worry about it. I'm just going to give you the answer. So there's only one radial force, and it's the electrical force. And we learned in Physics 121 that the electrical force is the charge of this, which is E, times the charge of that, which is E. So E is the charge of the proton, which is the same thing as the charge of the electron, over 4 pi epsilon naught r squared. So epsilon naught is just another constant. You see it a lot in electricity. Okay, great. So we can say this is equal to that, which it is, right? And we can solve for the velocity. Well, let's solve for the velocity squared. Okay? So let's solve for the velocity squared. So we're just going to have velocity squared equals E squared r all over 4 pi epsilon naught m r squared, right? And then what are you going to do with these r's? Goodbye. So you just going to get rid of one of them there. Okay? All right. So there you go. So that's the equation for the velocity squared. Okay, now this is the classical, right? Just what we learned in 121. But now remember, the electron acts like a wave, right? It acts like a wave. So when the electron is orbiting the proton, we got to do that, And it has to be a standing wave, because if it weren't a standing wave, there'd be like a disconnect, and that doesn't make any sense, right? Because it's orbiting, continuously, right? So an electron standing wave, oh my gosh, an electron standing wave. So wow, so how do we deal with that? Well, not too bad. So there has to be, okay, what's the circumference of a circle? 2 pi r. So 2 pi r has to equal some integer times lambda. Yeah, okay. So this is continuous. It's going to, always be connected. This is non-continuous, so you have a disconnect, which doesn't agree with the experiment. So we just have to say that there's n wavelengths in the circle, right? So 2 pi r equals n lambda. And again, n is just an index. All right. Okay. Well, now you can probably guess what we're going to do. What do we always do in quantum mechanics when we have a wavelength? We use a de Broglie relation, right? So we know that lambda equals h over p, which is h over mv. So now we're going to have 2 pi r equals n lambda, which is nh over mv. Now we can solve for v. So v is nh over 2 pi rm. Okay, all right, now I want to introduce something that just shows how lazy physicists are. So when you do quantum mechanics, you see this h over 2 pi like all the time, and you get sick and tired of writing it. And so what people do in the real world, I'm not making this up, is this is called h bar. So it's h bar. Okay, so whenever you see h bar, it's just h over 2 pi, just pure laziness or efficiency. Okay, so this is the same thing as nh bar over rm. Okay? Well, all right, let's square it. Let's square the silly thing. So we have v squared equals n squared h bar squared over r squared m squared. All right, so now guess what we're going to do? Now we're going to put this equal to that. Oh boy. Okay, so we're going to say that e squared over 4 pi epsilon naught mr equals that, n squared h bar squared over r squared m squared. And then kill that, kill one of those, multiply it up. So we can get r. What else can we kill? Oh yeah, kill one of those, kill that. Anything else? Nope. So we're going to have r equals n squared h bar squared 4 pi epsilon naught over e squared rm. Let's see if I did it right. Yes, I did. Yay! Oh, wait a minute. Oops, sorry, I didn't do it right. Okay. All right, that. Now we can simplify that a little bit, because remember, all right, so we can just do this, right? Okay, now look. Constant, 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 right? Everything is a constant. So why don't we just say this is equal to n squared times some constant. Look, this is the radius. This is a number. So what does this have to be? This is a radius in meters, number, no units. This has to be a length, right? A length, some kind of a radius. So we're going to lump this whole thing together, and they're going to call it A sub b. I don't know why they didn't call it R sub b, but they call it A sub b. A sub b. And guess what the b stands for? Bohr, all right? So this is the Bohr radius. And that's equal to n squared times 0.0529 nanometer. And again, your n is just our good old n, right? N equals 1, 2, 3, blah, blah, blah. All right. So what does that say? It says that the electrons can only exist at certain radii, right? So the radii, they're quantized. Only certain places, right? Only certain values of the radius can the electron exist. Well, that's kind of weird, right? You don't think of that in classical physics. In classical physics, you just think of the electron orbiting the proton wherever it wants to, you know? Well, quantum mechanics says, nope. Quantized radii. Quantized radii. Okay, so these are the allowed radii for the electron. Okay, now we might as well find the energy, right? Oh boy. All right, let's find the allowed energies of these electrons. Okay, so the allowed energies of the electrons, well, okay, so the total energy is the potential energy plus kinetic energy. And this is the potential energy to electricity. Okay, so that's, if you didn't take physics 220, don't worry about it. So let me rewrite it. You'll see why. So K plus UE, so kinetic energy is 1/2 mv squared. Okay, we learned in physics 220 that it's E squared, oh, or wait a second, yeah, over 4 pi epsilon naught R. All right, so now I'm not going to do the math, sorry. So skip steps, okay. So skip steps, put in all the values and everything like that, and this is what you come up with, minus 13.6 electron volts over n squared. All right, so I skipped the math and no more joules. Remember we had that when we talked about, right before we did the chapter on relativity, I introduced electron volts, and I said we were going to use these units in quantum mechanics and nuclear physics and atomic physics. Well, there you go, all right? Because it's ridiculous using joules. It's just, they're too small. I mean, a joule is too large. So there you go. So this is the energy of the electrons. And what do you notice? Again, there's only certain allowed values. Well, hey, we already saw that, right? We already saw that before, you know, with a particle in a box. So now we're applying the Bohr model to a hydrogen atom. Bingo, quantized energy. Quantized energy. So this is awesome. By the way, just for your FYI, 1 electron volt equals 1.6 times 10 to the minus 19 joules. Okay, so that's why we don't use joules anymore. Just joules too big. Okay, now some people, when they see this, they say, wait a second, what's the deal with a minus sign? Well, we talked about this in physics 220, but basically when you have a bound system, you just say that the energy is negative. When two particles, like let's say the electron and the proton, are infinitely far apart, we say that potential energy is 0 because there's no interaction. When they're close to one another, it's a bound system, and it takes positive energy to break them up. So we say that the bound system has negative energy. It's not a big deal, but that's really what it is. Okay, so as I've been saying all along, you know, look at that. This is what the theory says. And this is the, right? So you put for 1, you get minus 13.6, put 2, minus 3.4, and this all agrees with data. It all agrees with data, right? And so, I mean, here you go, right? Here's the model, here's the Bohr model. So you can figure out the radii of the electron, the velocity, the energy of all these different states. N equals 1, N equals 2. That's what you get. Now, some of that's right, some of it's wrong, all right? But the energies are dead on. Okay, so this is, oh yeah, okay. I already said this, but whatever. So let's say here we are in a n equals 3 state, and the electron wants to get rid of some energy to go to a lower energy level to the 2 state. And so you look at the energy diagram, and you get from a 2 to a 1, let's see, no, a 3 to a 1, that to that, right? And so minus 1.5 for the 3, minus 3.4 for the 2. The difference is 1.3, right? Right? That minus that is that. So this photon has to have 1.9, which I've already talked about. And so for the hydrogen, when it goes from the 3 to the 2, it's only going to have one specific energy, which means one specific wavelength, which means one specific color of light. And that's why you get a spectrum, you know? Okay, I already said this, that's okay. Here's an electron in the 2 state. It's going to absorb a photon to get to the 3 state. Well, again, what's the difference between the 2 state and the 3 state? 1.9 eV, right? And so what's going to have to be the energy of this photon? 1.9 eV. So, yay! All right. Okay, so it's great. All right. And also, so this says minus 13.6. That means it's going to, if you want to get rid of this, if you want to ionize this atom, in other words, knock off this electron, you have to have at least this much energy, right? So this is like the binding energy. But when you get further and further away, it's less and less energy to ionize the atom, to get rid of the electron. That kind of makes sense, right? I mean, just think of, here's a positive proton, negative electron is a strong force. Here, the distance is getting further and further away, so it's easier to get rid of the electron. Okay. Now, let's talk about angular momentum. So, classically, angular momentum is just, uppercase L, and it's the mass times velocity. That's just the linear momentum times the radius, right? So you're thinking of a circle, radius r, and the object's going in a circle. So the angular momentum is the linear momentum, mv times the radius of the circle. Okay, now think about it. According to the Bohr model, the radii are quantized in hydrogen, and the velocity is quantized in, well, not just hydrogen. In the Bohr model, the radii are quantized and the velocities are quantized. Well, here we have a radius and here we have a velocity. So what does that say for the angular momentum? It has to be quantized, right? It has to be quantized. So let's figure this out. Okay, so earlier we had 2 pi r equals n lambda. And of course that's equal to n h over mp, right? Because the de Broglie lambda equals h over p, which is h over mv. We use that all the time, by the way, in quantum mechanics, so it's worthwhile learning. Okay, so there we have it. Now we want to say L equals mvr. Okay, let's see. So we want, okay, let's see. Okay, so let's get rid of that. So we want mv, so mv, like that. And then divide by the lambda. And let's see. Oh no, I'm sorry. What did I made a mistake, sorry. Okay, let's do that again. So 2 pi r equals n lambda. That equals nh over mv. So therefore, L equals mvr. So mv is equal to nh over 2 pi r. That's what I wanted, right? So mv is nh over 2 pi r, but we have mvr, so it's just going to be nh over 2 pi, right? And again, we have that h over 2 pi, like I told you, so that's just n times h bar. Okay? So bingo! The angular momentum can only have certain values, right? So it can only have h bar, 2h bar, 3h bar, and so forth and so on. So just by using the de Broglie relation and this, we get that the angular momentum is quantized. There's only certain allowed values of angular momentum. Only certain allowed values. Okay, let's go back to the spectroscopy thing, with all the emission lines and absorption lines. Now you recall that we spoke about this way back a week or so ago in chapter 37 or something. And I indicated that people had no understanding, right, of the certain wavelengths for the absorption lines and emission lines. However, people didn't just quit, They looked at all the data and they came up with these equations. They had no clue why they worked, but they just basically fit the data to the equation. Well, that's pretty cool. I mean, it's not great, but it's not bad, right? It's kind of like plugging in data in an Excel spreadsheet or a formula, an Excel, and say, Excel, find the formula that fits all this data. Of course, they didn't have Excel back then. So it's still pretty cool. All right, now look. So that was this was the data, right? This equation was made from the data. Well, if the Bohr model is any good, the Bohr model should be able to come up with that equation, right? From basic principles. Okay, so that's the challenge. Okay, Bohr, figure it out. See if you can get it. Okay, now you notice I have this in yellow, so watch it, okay? So this from the data. So Bohr, and his friends, they worked it out, and they got this. Uh-oh. So the data said 0.18. Bohr, using his model, came up with 0.12. Now, I don't know about you, but I don't think that's much of a big deal. But hey, it's not the same. So if you're a good scientist, you got to see what's going on here, right? What's going on? Well, it's real simple. So this here result was formulated with hydrogen, right? So you have a proton in the middle, and you have an electron orbiting the proton. So this number was the result of assuming that the proton was stationary, okay? Well, that's a bunch of baloney, and you learned that in Physics 121. I mean, the electron and proton orbit a common center of mass. Remember that? Just like, when you learn introductory astronomy, they lie, right? They say that the sun is stationary and the planets orbit the sun. Well, I mean, the planets do orbit the sun, but the sun is not stationary. The sun and all the planets, they orbit a common center of mass. So the sun doesn't just sit there. The center of mass is not the center of the sun, but it's close to it. But all I'm saying is, if you do this correctly, you have to say that the proton actually orbits, the electron and the proton orbit the common center of mass, which is not the center of the proton. So when you do this calculation correctly, including that center of mass business, guess what you get? Ta-da! All right, so they nailed it. Okay, they got it. So the Bohr model exactly agrees with the formula that these people came up with just looking at the data. So that's a huge success, right? It's a huge success. All right, so think about it. Just pretend you're Bohr. You're doing great, right? Your model agrees with the data from hydrogen. Well, what are you going to do next? You're not going to just quit, right? You've got to see if it works with other elements. So what are you going to do next? Well, you want to go to uranium? No. You want to go, what do you want to do? So what Bohr did, he's pretty conservative. He's not a conservative. He's radical, totally radical. So what he decided to do next was hydrogen-like atoms. Well, what does that mean? A hydrogen-like atom. So, sorry, you're not supposed to see that. Okay, so what's a hydrogen-like atom? Well, again, hydrogen has a proton and a single electron, right? And so a hydrogen-like atom might have 2 protons and 1 electron. Whatever. It just has 1 electron. Okay? So that means like this. So you probably had this in chemistry. Helium plus. What's a helium plus? Helium has 2 protons and 2 neutral helium has 2 protons and 2 electrons. But if one of those electrons was kicked out, right, then it would be He plus. So it just means, this is helium plus. So 2 protons, 1 electron, okay? So it's ionized helium. That's all, okay? So basically what he's looking at now, or, lithium would be plus plus, right? 3 protons, nucleus, ionized 2 of the electrons. So basically he's looking at 1 electron atoms, okay? 1 electron atoms. So again, it's called hydrogen-like atoms. And he, just redid the analysis, and the only difference is with the Z. Okay, Z is the number of protons. Okay? So in other words, for hydrogen, Z would be 1, and you just have the same formulas as we had before, right? For helium, Z is 2. Okay? So he just did all that. And it worked great. So he had success with hydrogen. He had success with hydrogen-like atoms. So what are you going to do next? Then you're going to get brave and start doing atoms with like 2 electrons or 3 electrons and so forth and so on, right? Well, then his model didn't work anymore. All right, so So, I mean, I guess how should you look at this? Should you say he's just a big flunky? No! Again, he bridged the gap between classical physics and the modern quantum physics. And, you know, for hydrogen, he nailed it. He explained spectroscopy. He came up with quantized energy, quantized angular momentum, and that's still in quantum mechanics. So, you know, I mean, he did great. I mean, this is wrong. We'll talk about that soon enough. This is wrong. This is wrong. The energy levels are right. So he did great. All right, again, so there you go. All right. Oh, yeah. So, well, I don't want to talk about that yet. That's later. Okay. Okay, so we're done. Let's review. So we talked about the photoelectric effect experiment. And again, that was crucial because there was no possible way to explain that with classical physics. No possible way. So that was the experiment that forced people to come up with a new, you know, to come up with quantum physics. And it's, again, it's interesting that Einstein played a huge role, right? All right, so when you understand the photoelectric effect, you have to have a third model of light. So there's the particle, there's the ray, which is like the particle, there's the wave, and now there's the photon. Okay, so that was weird, right? Because we talk so much about the wave-like nature of light, and now we're saying it acts like a particle. But then what we saw, when you do the double slit experiment with photons, you produce a wave interference pattern. So you see, I mean, there you go, right? A chunk of energy producing a wave interference pattern. Okay, then things got really wacky. We saw that the de Broglie prediction that any massive particle acts like waves. And this incredibly important formula, the wavelength equals h over the momentum, h over mv. To recognize that the de Broglie standing wave of a confined particle requires energy quantization. When you confine a particle, you get energy quantized, so it's only certain allowed energy values. Then we learned about his stationary state model, how the model explained the spectra, and his hydrogen atom. Okay, so there's the photoelectric effect again, where you shine light on a metal. If the light has a frequency above the threshold frequency, the electrons are emitted. And Einstein explained it by saying light comes in chunks with this energy, hf, but F equals c over lambda. So again, this is a crazy formula because you're talking about energy of chunks having a wavelength. Chunks can't be divided like dirt. A piece of dirt is a piece of dirt. You can't have half a piece of dirt. The energy of one chunk is delivered to one electron. And then this was his prediction. You know, we talked about the V stop. And he predicted this formula, and by golly, the data matched it exactly. So that's why Einstein got the Nobel Prize. So here we have the wave model of light. We talked about that with interference and diffraction, the ray model with lenses and mirrors, and now we have the photon model. Light is made out of massless photons, travel in straight lines, speed of light. Here's the energy of a photon. The superposition of a large number of photons has the characteristic of a classical wave. Crazy. Okay, that's the de Broglie relationship, which again is insane because you have a mass, which is like a particle. Now you have wavelength, which is a wave, and waves and particles are supposed to be completely different, according to classical physics anyway. And you do the double slit experiment with electrons, and you get an interference pattern, which means that electrons act like waves, which is insane, but it's true. And then, so we put a particle in a box, one-dimensional box. The particle is stuck, and the energy, there are only certain allowed values of the energy. And I know I repeat myself a lot. We're going to see this again, so remember it, right? We're going to see this particle in a box with this formula again later on, a couple chapters from now. And then the Bohr model, like the first crack at quantum mechanics, I guess you would say. Got a lot right, got some things wrong. The Bohr model, matter is stable because they're stationary states, quantized energy. Atoms emit and absorb a discrete spectrum. Absorption wavelengths are a subset of the wavelengths of emission. So the Bohr model explained all this, which was clearly not understood before Bohr. And the energies between the states is equal to the energies of the photons, either being absorbed or emitted. Angular momentum is conserved. And that's it. Thank you very much.